Okay, this lesson is for section 3.4, which is on the chain. Pause this anytime you need to write down things that you see in the paragraphs or different examples that you may want to write down. What the chain rule is used for is when your function is a little bit too complicated to use just the standard rules that we have. So here's some examples, and let's take a look at them. In this function, you would easily be able to get its derivative, and it's just 2x. But over here, we're going to need the chain rule, because you cannot just say that this derivative is the square root of 2x, because it is not. So because this has a square root on it, we're going to need a chain rule to find this derivative. Sine x is fine. Sine x we can find a derivative of. You know, it's cosine x. This is not just cosine 6x. Because of the 6x, this function is more complicated, so we're going to need the chain rule. Again, you can find this derivative, but for this part, because it's raised to the fifth, we need a chain rule. And this derivative is just e to the x plus secant squared x. This, we need something to take care of the fact that the angle is x squared and that the power is actually another function of x in and of itself. Okay, so there are different ways to write the chain rule. This right here, I'm going to box this in. You want to know that this is the most general form and probably the most useful and most common form of the chain rule. So you're going to use it when you know that y is some composite function, f of g of x, like on the last page, sine of 6x. The 6x would have been your g of x, and the sine of would have been your f. So the chain rule says that the derivative of f of g of x is f prime of g of x. So again, sine of, well, we're going to do those examples in a minute, so I'm not going to talk through that whole thing. But this is what we're going to, this is the most, again, general form of the chain rule. Another way to write it, you'll see, is right here above, above this. And sometimes you have something that's even more complex. Like you might have, for a function, y equals the sine cubed of 4x squared minus 1. Okay, in that case, we might have f, to get our derivative of this, we might want f prime of g of h of x times g prime of h of x times h prime of x. Or in the notation like above here, we would be splitting this up into three things, where y is a function of u is a function of maybe some other variable. Y would be written in terms of u's, u would be written in terms of v's, v's would be written in terms of x, and then we would have dy dx is going to be this derivative, dy du, times this derivative, du dv, times the last derivative, dv dx. This might sound like, you know, kind of too vague right now, but once things are less generalized, when I give you some examples, they'll be easier. But you can see how the du's go away, the dv's go away, and how you would just be left with dy dx. One last way, one last thing you want to realize that they sometimes use for their notation is they'll call g of x a u. So whenever you're finding the derivative this way, you want to say, okay, we're going to be finding f prime of u, and then multiplying that by u prime. Okay, I want to try these two first. Hopefully you have the chain rule written down. If not, you might want to pause this, go back, and make sure you have the chain rule written down. I'm going to use them both ways. Let's call the red one number 1. Okay, so for this, there are two ways I'm going to show you both, and you decide which one you like better. First, I'll do the longer one. I can rewrite this as y equals the sine of u, which is obviously going to force u to equal 6x. Now the chain rule says I can find both derivatives, so find the derivative of sine u. That's going to be dy du. So dy du equals cosine u and du dx equals the derivative of 6x. And the chain rule states that you have to multiply those two derivatives together. So dy dx is going to equal dy du times du dx. And then when you put them together and write them neater, I'm going to move the 6 in front, and I'm also going to replace the u with what u equaled. Cosine of what u equaled, which was 6x. Okay. Now the other way that I can look at doing this problem is just by saying that this was f of g of x. So the derivative of f of g of x is just going to be f prime of g of x times g prime of x. G prime of x is the derivative of 6x squared, and the derivative of 6x squared is 6. Okay, now the second one I'm not going to write down the explicit, what u would equal and what y would equal. All I want to do with this one is, and I'll call this number 2, is just tackle each one of these as an f of g of x. So this is like an f of g of x. So my derivative is going to be, and I'm going to leave some room in front. I'm going to leave a little bit of blank space and then go the derivative of e to the x is e to the x. So the derivative of e to the u would be e to the u, but now we need times u prime. Okay. The derivative of tangent x is secant squared x. So the derivative of tangent x squared is going to be secant squared of x squared. But now we need to multiply, this is supposed to be a squared. Now we need to multiply by the derivative of x squared as well, which is 2x. So the 2x is going to be right out here. Alright, so just to recap, this was the derivative of e to the u is e to the u times u prime, and the derivative of tangent u is secant squared u times u prime. Now, we can generalize the chain rule into the general power rule for algebraic functions, and I want you to see. Okay, there are 3 ways that you can write down the general power rule. My preferred way is over here that I wrote in orange. If you have a function of x raised to a power, you just bring the power down. This is going to look just like the power rule that you're used to. Bring the power down times the function to the 1 less power, but now we have this extra piece, times the derivative of the function. What you never realized you were doing when you were finding a derivative of, say, something like, let me pick a good color here. When you were finding the derivative of, say, x cubed, its derivative was 3 times the x to the 1 less power times the derivative of x. But we never needed to think about it because the derivative of x is just 1. But now we're going to need to think about that extra part. So let's look at a couple examples. Okay, now I copied and pasted the general power rule right here. So what we're going to do is find the derivative of a quantity to a power. So do you see how it fits this rule? That's my function of x, that's my f of x, to the nth power. So using the general power rule, which is really just the chain rule, we bring the power down. It's going to come in front. The power is going to be decreased by 1 from this quantity, and then we're going to multiply by the derivative of that quantity. So we bring down the 3. We have the same quantity to the 1 less power, and then you multiply by the derivative of the quantity, 3 minus 4x. And there's really not a lot you can do to simplify this. You may want to take the 3 through here. You might just want to write things in a different order. So I'm going to just distribute the 3 through and make it 9 minus 12x. And then I still have the quantity 3x minus 2x squared, quantity squared. Okay, let's try on these. I do want to do this one first. Okay, so for the first one, it's clear what your exponent is. So your y prime, or dy dx, is going to be, we're going to bring the exponent down. Then our quantity is going to be raised to the 1 less power. And then we're going to multiply by the derivative of the quantity. So, what is that? 5 times 3, 15 times 3x plus 2 quantity to the 4th. That's it. Think about what the alternative would have been, by the way. If you didn't just do this, you would have had to multiply this out. 3x plus 2 times 3x plus 2 times 3x plus 2 times 3x plus 2 times 3x plus 2. Multiplying all those quantities and getting a really big long polynomial. And in the end, when you took the derivative, it would have been the equivalent to whatever this is if you would have expanded it. So chain rule is definitely the way to go. Okay, so let's call this one number 2. Okay, so for number 2, you might, it helps some people to rewrite that as a quantity raised to a rational exponent. So do that if you need to. That's raised to the 1/2, right? It's the inside power over the index, and since that's a square root, the index is a 2. Alright, so your derivative is going to be bring the power down times the quantity to the 1 less power times the derivative of the quantity. Now this time a few things happen. One is this 2 and this 2 cancel because I don't have any quantities. And the other thing is because this whole thing is raised to a negative exponent, I'm going to want to move it. It's on the top, so now I want to move it to the bottom so that my exponent isn't negative anymore. Okay, so what do I have on the top? All I have left now is this x. And now on the bottom, I'm going to have x squared plus 1 to the positive 1/2. Or if we make it look more like it did the way the problem was given to us, we could put that back in radical notation. And that is the derivative of this.